Does this work? Okay. It's a great honor to be here to memorize Shoucheng in the way of a workshop to explain physics to him. I was a student of Shoucheng during 2012 to 2017. And actually, as I shared with some of you last night, I met Shoucheng much earlier when I was still a freshman in 2009, when I wrote a letter about some of my physics studies, and Shoucheng really replied me, and then we began to know each other and began our story. And I had a lot of beautiful memories with Shoucheng. Including, so this is my graduation in 2017, and after my graduation, in that year I also got married, and Shoucheng and Barbara invited me and my wife to Kabul, and we had a great time there discussing physics and beyond physics, and this is on Stanford dish together with Brian. We had a nice photo. So during my study, the most important thing I learned from Shoucheng is I guess, not only physics but also philosophy. In particular, how to ask a simple and deep question, how to do beautiful physics. So in this sense, I think Shoucheng is really not only a physicist but a true philosopher. And in the ancient sense, actually, Shoucheng is a master of all kinds of science and beyond science. He really thinks deeply about human beings. So, and this is his favorite painting, The Schools of Athens by Raphael. There's these giants, and now Shoucheng is with them. So, yeah, today I'm going to talk about a recent study we had. It's a generalization of SYK model, which Subir mentioned, to chiral Majorana fermions. Unfortunately, I didn't get a chance to tell Shoucheng this idea. I hope he will appreciate my idea. So this work is in collaboration with Shuai and Jinbing Yang back at Stanford. So Jinbing is actually a very brilliant student who is coming to Stanford as a SITP fellow, and I learned a lot from him about SYK stuff, which makes this work possible. So so first I'm going to briefly review Majorana fermions and the SYK model, and thanks to Subir already gave an introduction, so I don't need that much introduction. But I do want to mention, so Majorana is another scientist which Shoucheng liked a lot. He did the beautiful work of Majorana equations, generalizing fermions to charge neutral fermions, which is antiparticle of itself. And after his great discovery of Majorana equation, so Majorana disappeared mysteriously at his brightest age, and unfortunately Shoucheng also left us at his brightest age. During Majorana fermion is originally proposed in high energy physics, but it plays an important role in condensed matter physics afterwards. Especially there are many models, some of them beautiful ones proposed by Kitav, that the Majorana fermions can also exist in condensed matter systems, and in particular we have chiral Majorana fermions in 1+1D, which can be the boundary of topological states, and also Majorana zero modes, which are anions, non-abelian anions, which are related to non-abelian anions in a P plus IP topological superconductor. So during my last few years of PhD, I actually worked a lot with Shoucheng on how to realize P plus IP superconductors and chiral Majorana fermions. So like this is a proposal we had on how to realize the P plus IP superconductor, and this last work in last year I had with Shoucheng on chiral Majorana fermion is about how to the possibility of implementing quantum computing with chiral Majorana fermions, which Shoucheng actually was quite excited about. Since I was stayed at both Stanford and Princeton, I heard a lot about SYK model, which is also has a Majorana version. I was working on chiral Majorana fermions, so I thought maybe I could study chiral Majorana fermion SYK model. So this is how the idea comes. So the original SYK model is in 0 plus 1D. It's about 0 plus 1D Majorana fermions. We have a random Q fermion interaction among them, where the interaction obeys this random distribution weighted in this way. So in 0 plus 1D, the fermions have dimension 0. So this makes the interaction relevant at low energies. So this is really a strongly interacting system in 0 plus 1 dimension. And it was shown that by these, initially proposed by Kitav and studied by many others, including Subir. So this model has a nice duality to the ADS2 space with a black hole. Actually, we now know how to draw a black hole. Yeah, this is a black hole in ADS2. This nice model has lots of property due to this ADS2 space with a black hole. So in particular, at low energies, this model has an asymptotic conformal symmetry. Basically, it's a symmetry upon reparametrization of the time. And upon this, this basically restricts the form of the endpoint function of this system. So if you look at the Green's function of the system at low energies, it behaves as a power law, which is a conformal behavior. And this also gave you the effective action, which is Schwarzian term, which is actually a conformal anomaly. An interesting feature of this model is it exhibits a large ground state entropy proportional to n. So n is the number of Majorana fermions you have in your system. So this implies you have a spin glass ground state, kind of a spin glass ground state. And in particular, this is a kind of due to a black hole, near extremal black hole in the ADS space, and where this entropy can be interpreted as the black hole entropy. Another remarkable feature it has is the. You have a question? Oh yeah. Okay. Yeah. The ground state is not unique there. Yeah. So it's a zero temperature entropy. So another remarkable feature this model has is the chaotic behavior it has. So in classical mechanics, we know that the chaos, one of the features of the chaos is when you have two classical orbits, and when they evolve as a function of time, if initially they are nearby, then after a certain time, they will depart from each other exponentially in time. So classically, this is just a partial xt or partial x0. If we want to evaluate for a quantum model, a natural generalization is to consider, so this can be written as a Poisson blanket and we convert it to a commutator in quantum mechanics. And if we expand this, actually there is a term which is known as the out of time autocorrelation operator. If you have a chaos in your quantum model, this term will also give you this exponential behavior which resembles the classical chaos behavior, the Lyapunov exponent. So in the SYK model, this actually we can calculate OTOC, which is the out of time autocorrelation of the fermions, and one would find there are piece growing exponentially with time, and this defines a Lyapunov exponent, and this exponent is actually approaching 2 pi over beta, which is shown by Messina, Schenker, and Stanford, is a maximal chaos bound of Lyapunov exponent in quantum chaos. So there has been lots of studies of SYK, and in particular also higher dimensional generalization of the SYK model. For example, some of the models are generalizing it by assuming assuming a chain or array of SYK clusters. Like Biao Lian and Hong also studied this, and also there are other field theory generalizations. This is Berkus, etc. They generalize this to non-chiral 1+1 dimensional fermions, so which is also known as the theory model in high energy. But in this model, they showed that the interaction is actually irrelevant, so there's no interesting physics at low energies. And there are also other modified non-chiral fermion boson models. These many people studied, including Subir also studied that. So actually, this is one main difficulty in generalizing to higher dimension. That is, the interaction often becomes irrelevant, and you just get a Fermi liquid behavior. So now I move on to the chiral Majorana fermion discussion. So I had this idea that what if we consider the boundary of a set of p plus IP topological superconductors and add interactions among them? If we have a large number of them, it's naturally a SYK model of chiral Majorana fermions. So naively, classically, we could, if we think of these fermions, they're moving constantly in one direction. This just looks like a traveling version of the SYK model. And also, this is kind of interesting because we can look at the chaos behavior of topologically protected states. The chiral fermions should be, on one hand, topologically protected, but on the other hand, it could have interactions and chaos, etc. So it will be interesting to examine what they are. So this is a model I wrote down. So basically, we have these fermions, n flavors of chiral Majorana fermions with the same velocity. This is makes this thing simpler. And also I add a random interaction, 4 Fermi interaction among them. They also obey this random distribution. So if we count the dimension of this interaction, actually this interaction term has both scaling dimension 2, but also conformal spin 2, basically because these fermions are chiral fermions. So actually one can show that because of the model is purely chiral, this interaction here is exactly marginal. And that's actually a very unique property which makes this model exactly solvable, as I'll show later. And also because this term has conformal spin 2, it breaks the Lorentz symmetry. You don't have boosted symmetry anymore. But this is allowed in condensed matter. So to define this model, actually there's a subtlety I want to mention, but I want to go to details. Because of the loss of Lorentz symmetry, when you define the product of two operators, you need to specify your point splitting direction. That is no longer invariant under Lorentz transformation. So, so in condensed matter, the direction of splitting is usually in x direction, which has a natural explanation because we have a natural cutoff, lattice cutoff, that serves as a point splitting at high energies. So just for that, we need to keep in mind that whenever we consider product of two operators, we need to consider them as limiting, approaching each other in the x direction. And this leads to the commutation relations of these operators. And this is actually, because psi I, psi j is actually the generator of SON Kac-Moody algebra. This is just the SON Kac-Moody algebra. So, but the x direction, so partial x is specified by the point splitting x direction. So for angle to 4, this model is actually pretty familiar to all the condensed matter physicists. It's basically just the chiral Latinger liquid with spin charge separation. So basically we can redefine the 4 chiral Majorana fermions in terms of complex fermions of spin up and spin down. Then this model is just a this kinetic term is a chiral fermion, 2 chiral fermions with a single interaction term. For 4 fermions, you only have 1 interaction. So we can Bosonize this model to solve it exactly. It's an integrable model. So by doing this Bosonization, we arrived at 2 free bosons with this action. And if we redefine the basis into this one, we can rewrite them as 2 decoupled bosons with 2 different velocities. 1 is 1 plus minus j over 2 pi. So this is actually the spin and charge mode in a spin charge separation story, and these two velocities are the spin and charge excitation velocities. And in this example, we also see that j is actually exactly marginal. It only modifies your velocity. This actually gives you some bound on this interaction j, because we know that if j is smaller than 2 pi, then nothing is wrong. But if j is greater than 2 pi, we have one of the velocities flipped, so the chirality is flipped. This is actually non-physical in condensed matter, because the chirality is protected by if you have a bulk topological state, it should be protected. So the physical understanding is, if you want to study j greater than 2 pi, you need to add some higher energy regularizations, which reverses these velocities back. But here we shall not study this, because we don't want to complicate the problem. So we shall just restrict ourselves to interactions bounded by 2 pi. Of course, this is just for n equal to 4. So for n equal to 4, we can also quickly examine the fermion 2-point function, which can be obtained from the Wick's theorem. It takes this form. And if we also look at the OTOC of this intergroup model, we shouldn't find any chaos. And indeed, this is the 4-point function. So out of the 4-point function just to show exponential decay instead of exponential growing behavior. And one can see that in the 4-point function, we can see that only this cone is affected, which is actually the causal cone of this model. So now you can look at the large n case. For the large n case, the interaction, you have lots of interaction, but for people who are familiar with SYK model, because we have a large n, we can count just the contributions of the Feynman diagrams to the Green's function to the leading order of 1 over n. And this gave us the so-called Mellon diagrams. So these diagrams contribute to your 2-point function, and you can summarize this thing as a self-energy, and then you just have a Schrödinger Dyson equation, which can be written in this form. So this is just saying that G is the self-energy is just the 3 pieces of Green's function, and also then this formula just says this line. So different from SYK, the 0 plus 1D SYK model. In this case, the entire Schrödinger Dyson equation is actually exactly scaling invariant. So if we do such a scaling, we can verify this. This again says that J is exactly marginal, and actually this term is indispensable in this case. So if we make a comparison with the original SYK model, there's a difference. In the original SYK model, we can simply ignore this term because the self-energy is more relevant at low energies, if we consider low energies. And by ignoring this term, we can have a reparametrization symmetry under this tau goes to f tau. This is the transformation. But for two-dimensional Chiral SYK, you cannot ignore this term, and this actually you don't have the reparametrization symmetry, but you just have one scaling invariance. But still, making use of the scaling invariance, you can get some very interesting results because the scaling invariant actually allows you to propose an ansatz for the self-energy and Green's function. So if we write the omega and k in terms of polar coordinates, we know that self-energy and G will be proportional to kappa and 1 over kappa respectively, the norm in momentum space. So the only unknown part is the angular dependence of the self-energy and Green's function. So we can, after this ansatz, we can substitute this ansatz into the Schrödinger Dyson equation, and what we get is just a differential equation of one variable. So we can then solve this equation exactly, and actually that gave you this self-energy and Green's function solution. If we look closer at this 2-point function, actually, amazingly, we find this large n two-point function has exactly the same form as the n to the 4 case if we go back. And also, we have these two velocities appearing here and there. So this is for 0 temperature. And these two velocity again is related to 1 plus minus j over 2 pi, but j now is the average of all the random couplings. And also, we know that this form is just like a product of two SY, 1D SYK models along these two directions, different directions. So again, so this means we also need this physical bounds, the j is smaller than 2 pi. And if we look at the spectral weight of this Green's function at a fixed momentum, that just means it takes such a shape, which is this form. So that means all the eigenstates are actually all the eigenstates are confined between energy u minus k and u plus k. So for non-zero temperature case, actually the temperature sets a energy scale, and you can no longer use the scaling invariant answers. But actually, the fact that the 0 temperature solution has exactly the same form as n to the 4 and double SYK motivates us to test whether the finite temperature solution of n to the 4 or double SYK is also a solution for large n. And it turns out that if we substitute this into Schrödinger Dyson equation, this is a Fourier transform of it. You need to see this piece, indispensable piece here. So actually, it indeed satisfies the Schrödinger Dyson equation. So in this way, we also find the non-zero temperature solution exactly. So this allows us to calculate the thermal quantities, for example, the energy density, just given by these two velocities, and the thermal entropy density. S0 is the 0 temperature entropy I'll talk about later. We can also look at the energy current, and remarkably, the energy current is still quantized. Actually, maybe not that remarkable, because in condensed matter we know that there's a quantity called thermal Hall conductance. Thermal Hall conductance, which is a topological invariant, and that should also be quantized to n over 2 in this case, if you have n chiral Majorana fermions. So so then about the 0 temperature entropy density. So because we have the exact solution, actually we can substitute into the effective action and to the leading order. This is just the easier way to calculate it. We can actually calculate this exactly, and surprisingly, the ground state entropy density is actually 0. And there's a physical picture for this that is based on this spectral weight picture, because we have shown that all the energy eigenstates are between u minus k and u plus k. Actually, this implies your partition function is bounded by a partition function of n free chiral Majorana fermions with u minus, velocity u minus, and a free model with velocity u plus. Yeah, okay, sorry. Yeah, so this is just a, sorry. So that means the ground state entropy should be the same as n free chiral Majorana fermions. I don't have much time, but I'll just show the results. So you can also calculate the OTOC. Basically, once you have the 2-point function, you can calculate this following basically exactly the same procedure as the 0 plus 1 DSYK model. And this will give you the chaotic behavior of the system. So I'll just show the result. So in general, it gives you the exponential growing piece of the OTOC in this form, where chi is this function. So this integral can be evaluated by a set of approximations, and sometimes saddle point contribution dominates, and sometimes the pole contribution dominates. So what you find is this is a kind of like a butterfly cone of the model. It's a tilted butterfly cone. So I also draw this u plus and u minus. They are the boundary of the causality cone, and both of these shadowed regions are the Majorana are the kind of the butterfly cone where you have exponential growth along a constant velocity line. So this is general behavior. But these two regions are dominated by dominated by pole contribution, which is takes this form, and in this region it takes a different form. So this is the velocity dependent and the Lyapunov exponent. You can show it. So yeah, so in particular, maybe I missed it. So one thing we note is that when j goes to 2 pi, approaching the maximal bound, you actually also approaches the maximal Lyapunov exponent 2 pi or beta. So okay, so finally I just want to mention that you can show that for other small n, actually for n smaller than 6, you can always solve it exactly by Bostonization. It also becomes free boson problems in some bases of fermions. But for n greater than 7, it becomes increasingly complicated. So we actually had a conjecture that when you increase this number of flavors, you should have a transition from integrable to chaotic at a certain n, and this n is probably maybe just a 7. And if we, for example, experimentally, if we consider thermalization of the edges, it will make a difference between integrable and chaotic. So yeah, this is just I want to say for Fermi surface. Yeah, so the large and chiral fermion model actually has an analogy with a piece of interacting Fermi surface, because we have, if we look at a piece of Fermi surface, we have a chiral fermion along this k perpendicular direction, but then we also have this k parallel degree freedom, which serves as a larger degree freedom. Of course, the interaction here is not that random, but I just want to mention this possibility of relation with Fermi energy. So I just conclude my talk and show this nice photo I like with Shoucheng. And because today is May the 4th, and Shoucheng is the master of nature force, I want to say, Shoucheng, may the force be with you. Thanks.
Nice talk. I can see a question here. You have a microphone.
Yeah, nice talk. So, so since now in your 1+1D SYK like model, you know, the random interaction term is marginal. That's different from the original SYK model. So my question is, what happens if I include this quadratic term into the term? Does it have a different property?
Yeah, we didn't study it in detail, but I have an argument on that. So basically, for chiral fermions, if you have a quadratic term, that is just a spatial rotation of your bases. So so because all the interactions are also point-like interactions, so you can choose your bases into the new bases, and that would just I guess the physics will remain roughly the same. Yeah.
If you put this model on a circle, then give a periodic boundary condition, then the free fermion does have a zero temperature entropy. So I'm wondering whether your model will also have a zero temperature entropy.
Yeah. So I didn't say it's actually. So what I talked about is ground state entropy density. So the density is still zero if you take the large.
Can you calculate the zero temperature entropy in the case of?
Yeah. So if you have a periodic boundary condition, then it's just a n log, I guess, n over 2 log 2. So the ground state entropy it's the same as the n free chiral Majorana fermions.
So it's independent from the coupling.
Right. So for any interaction, it's always 0. That's actually a very remarkable feature.
Yeah, actually, so you have many chiral fermions. I mean, I would imagine after Bostonization, for example, you would have a lot of different modes with different velocity, but now you only have 2 modes eventually. Two velocity.
Yeah, actually, so my guess is you still have many velocities, but maybe what happens is they are peaked at u plus and u minus. That's why.
So again,
maybe they are peaked. If you look at the distribution of your velocities, yeah, that's an unsolved problem. But my guess is all the velocity will be peaked near u plus and u minus. So in the larger limit,
then the Green's function is still only
yeah, sure. Yeah, this is the Green's function. Yeah. This is exactly the same as Inca 4. So for Inca 4, indeed, it comes from the just two modes. So it's actually So actually, I had some thoughts on this, because why the 2-point function is exactly the same as Inca 4? Because for Inca 4, you have a SO4 symmetry, because you only have one interaction, and for large n, you kind of also recover a SON symmetry.
Right, but so what about for n equals 6? I mean, you have some
n
equals 6, right?
I didn't show it, but for n equals 6, it will be 3 velocities. So
okay.
it will be different.
So chiral Majorana fermion excitations on the superconductor will have a finite lifetime. How will your results change because of that?
Finite lifetime, you mean?
So these are
You mean the
quasi-particles with
coherence?
some lifetime, yes.
Yeah, I guess, yeah, because it's a chaotic model here, I guess it will certainly become decoherent very soon. That's why it's chaotic, right?
Oh, no. When your starting model already has quasi-particles with a lifetime, and now you have interactions on top of that. Does that change?
You mean want to add a non-Hermitian part to the?
Mm-hmm.
I see.
Yes.
I see. Yeah, that I haven't tried yet. So yeah, that's a very interesting.
So it's
question.
distinct from a Fermi liquid from that point of view, right? Because Fermi liquid quasi-particles can become long-lived near the surface, but not for the superconductor.
I see. Thanks. Yeah, that's a very good point.
So we can have 2 more questions. I don't know who was first here. Maybe you start.
A simple question. So if you consider the corner almost whole edge, you have a chiral complex fermion. What will change in?
Yeah, the complex version of this model. Yeah, so in that case, you can also add a chemical potential term, but my guess is the physics doesn't change much. Actually, the chirality of this model actually restricts a lot of physics, like the ground state entropy. I think it's also related. So if you add a chemical potential, that's just as I just said, it's just a change of basis as a function of x. Right? You can eliminate that term, the chirality term, by just the rotation of basis as a function of x. So after the rotation, the interaction, I guess, doesn't change much, and the physics, I guess, remains largely the same.
If you didn't have the interaction, then this chiral Majorana is like moving on a single line in the space-time. So it's somewhat like a 0 + 1D system. And this interaction looks local, but because of the point splitting, it's actually coupling between these different lines at different t minus x. So can I somehow map this to 0 + 1D Majorana with coupling between neighboring blocks?
Yeah, good question. And so actually, classically, one would thought that this is pretty analogous to 0 + 1D. But what happens in 1D is that two fermions can really go away from each other on their interaction. But in 0 + 1D, they have to stay at the same point.
Yeah, so it's like a coupling between different blocks. So you know there's this chain of Majorana.
So I mean, just like a lattice version of this.
Yeah.
model.
So can this be somewhat mapped to this lattice Majorana?
Yeah, because you can't write chiral fermions on like 1D lattice. Maybe a 2D lattice is necessary.
No, I mean the t minus x as a block instead of. So it's the interaction is between the blocks, but the hopping is.
It's not true here because actually, yeah. As I showed that actually the Green's function actually looks like 2SYK along these two directions. That could be possible, that you can maybe in some way understand it as 2SYKs along this direction and that direction, but not the x = t direction. Thanks.
Okay, so I think we thank you again for this nice talk.
Thank you.
And